today's class. I'm just gonna review a little bit of what I was talking about on Monday, and then we'll do one or two constant strain triangle examples. Just a reminder of what we are doing for the last part of the course. We are actually doing both some of the theory and some of the coding for the linear elasticity, just to remind you of, sort of the three chunks of the course. The first part was the 1D elasticity and heat transfer. And that was just a way of introducing all the concepts, the strong form to weak form, the discretization, and then getting the system of equations. So that was sort of the first third of the course. Then the second third of the course was in 2 dimensions, but only the heat transfer. And the reason why we did the heat transfer only in the second part of the course is because we were already introducing a lot of things related to the discretization in 2D, which is a little bit more complicated than the discretization in 1D. And also because of all the vector calculus that you need to remember that you might have seen before, but we needed to sort of revisit that a little bit. So that's what we did in the second third, again, with the same structure. So strong form to weak form for the heat transfer problem, finite element discretization in 2D, put them together, you get a system of equations that you can solve to get the temperature at the nodes. And then the last part of the course is linear elasticity. And for this one, again, same topics, but now I'm kind of rushing through some of the theory, and then I'm gonna focus more on some of the examples, and then some of the practical considerations for abacus. So for the strong form of linear elasticity, it's basically like solving 2 heat transfer problems at the same time. This is sort of sum of forces in x equals 0. You can think of that as that, but it looks very similar to approximately sum of forces equals 0. And this one is basically approximately sum of forces in y equals 0. It's not exactly sum of forces in y equals 0, it's the divergence of the stress y component, but this can be thought of as sum of forces in y equals 0. And you can see that it's very similar structure to the heat transfer problem. So divergence of this traction vector sigma x plus some body force bx equals 0, divergence of the traction in y plus the body force in y equals 0. Also similar to the heat transfer problem, there's a relationship between stress and the gradient of the displacement. This is the material response. And again, if you compare this with the heat transfer problem, in heat transfer, you get the flux is proportional to the gradient of the temperature. Here you get the stress is proportional to the gradient of the displacement. And boundary conditions of either natural boundary condition type, if you know the force, or essential boundary condition if you know the displacement. So that's the strong form. If you solve that, what you get is the displacements over the domain and the stresses. And that's what you typically have been doing on abacus to try to know if something will fail or not. To solve this with FE, what abacus is doing behind the scenes is not solving directly the strong form, but it's solving the weak form. I'm not showing the steps, but basically you multiply by the shape function, you integrate, and then you do integration by parts, and then you end up with a term that looks like this. So gradient of the shape function times this D matrix, which just has material properties, times the gradient of the displacements. That will give rise to the stiffness matrix. You get an integral over the boundary of the weight function times the tractions or forces at the boundary. This is basically the natural boundary condition force vector. And this integral of the weight function times the body force, that one is the force vector associated with body forces, like gravity, for example. And then, as usual, the essential boundary conditions are stated in the, so the U's have to satisfy the essential boundary conditions, and the W's are 0 for the boundary where you have essential boundary condition. So same structure as before. All right, so that's the weak form. Then for the discretization, similar to before, anything that we discretize with finite elements has this type of structure, right? So the discretization of a function is the sum of the shape functions times the nodal values. The difference here with respect to heat transfer is that this is a vector and not a scalar. So it's a vector U, so it has two components. So the ux is the sum of the shape functions times the x component, and the uy is the sum of the shape functions times the y component. So that is the difference with respect to heat transfer, one of the differences. The other difference is that because u is a vector, when we think about the gradient of u, that one looks a little bit different from what we were doing for the heat transfer problem. This is the strain. And actually the gradient of a vector is a matrix, but it's a symmetric one, so we can arrange it in a vector form. And all you need to know is this form right here. I mean, this is the definition of the definition is this one. And if you use the finite element discretization, again, usually, for example, partial of ux with respect to x is just the sum of the partials of the shape functions with respect to x times the x values of the displacement field. So same idea of anytime you're interpolating a function, you basically are summing shape functions times nodal values. And if you're interpolating derivatives, then you're summing the derivatives of the shape functions times the nodal values. And again, the difference with respect to the heat transfer problem is that this gradient, it looks a little bit different because it's the gradient of a vector field instead of the gradient of a scalar. Okay, so that is the finite element discretization. If you plug this discretization into the integrals here of the weak form, what you end up with is you end up with the definition of the stiffness matrix and the force vectors. So the stiffness matrix at the end of the day contains basically the gradients of the shape functions times the material properties times the gradient of shape functions. Recall that this B matrix so this has gradients of, right? Basically the B matrix just has per column, every column is going to be for example, the first column is this gradient S of N1. And so on. So the B matrix will have the gradients of the shape functions, such that when you put them in a matrix and you do the matrix multiplication, what you are doing is basically the different products of the gradients of the shape functions. Again, this is very similar to what we were doing for the heat transfer problem. It's just the gradient looks a little bit different. So this is different from the gradient that we use in heat transfer. And it's given by this, right? So it's not, it's a little, that's why it's a little bit different. It's not just, the gradient used in the heat transfer problem is just these two. But the idea is similar, and you need to integrate that. And to do the integral, you can either do Gauss quadrature, you can do the integral analytically in some cases. I'll show for the triangle, you don't need to do the integral. For the body forces, again, the body forces, the force vector due to body forces is just the integral of the shape functions times the body force vector. The force vector due to boundary attractions is just the integral over the boundary that has the applied forces. And then if you assemble your stiffness matrix and force vectors into the global system, then you end up with your usual system of equations. So the global stiffness matrix times the displacement vector, which has all the nodal displacements, equals the body force plus the traction force plus reactions. Any questions up to this point? So like the big overview of how to go from the strong form of linear elasticity all the way to the system of equations. All right. So again, hopefully this sort of rings a bell to what we were doing for the heat transfer problem. Now, one thing to notice, this thing is the same no matter what element you use. The stiffness matrix is always calculated like that. The force vector is always calculated like that. So what changes when you use different elements? What changes is the number of shape functions and the specific form of the shape functions. So it will change your B matrix if you're using triangles versus quadrilaterals, linear versus quadratic. It will change this NE vector, it will change this NE vector. So even though the definition is the same, for every element, because you have different shape functions, the actual matrix is a little bit different. We are going to do it for the constant strain triangle. For the constant strain triangle, the shape functions are the ones that we have used before. I don't think I put them in slides, but there's some shape functions that are directly functions of xy. I don't remember by memory, but they are in some of in previous notes. We have an explicit version of the shape functions in terms of xy. And because of that, we can easily get the different derivatives. So when you put those shape functions and those derivatives into the integrals here, then we can get an explicit representation for the B matrix. So again, the B matrix, you just need to trust this one, where each one of these is just so y23 is just y2 minus y3 of the element. And so on. So again, this B matrix comes from the fact that we have an explicit definition for the shape functions and the derivatives. And when you put that into this with all the different shape functions, what you end up, if you just put it in the different columns, what you end up with is this description. The comma denotes, maybe I should make, so comma denotes so n1 comma x is just the derivative of the first shape function with respect to x. Actually, I don't know if you use that notation in vector calculus, the comma, yes? Right, a very common notation to avoid basically using the partial, you just say comma. N1 comma x is just the derivative of n1 with respect to x. So two things to note here is that obviously the specific, n1 comma x and all other derivatives are particular for this triangle. Again, if you have quadrilaterals, for example, you would have a different shape function. That's one thing. And then the other thing is that what is the size of this matrix? This matrix is always 3 rows, but the number of columns depends also on the element. So for triangles, this is 3 by 6, because this is 2 times the number of nodes of the triangle. So note the difference with the heat transfer problem. So what was the dimension for the B matrix of the heat transfer problem for the triangle? Anyone remembers? Yes. 2 by 3? Yes, 2 by 3. It was 2 by 3 because the gradient only had these 2 components, this derivative with respect to x and derivative with respect to y. And the 3 was just because it was a scalar problem. So we only had, temperature, temperature, temperature. So in the heat transfer problem, this is because the gradient was just dn dx, dn dy. And the 3 was because we only had basically, it was a scalar problem. So we only had T1, T2, T3 for the nodal values. The 3 by 6 comes from the 3 comes from the fact that the gradient has this sort of different structure. So the 3 comes from the gradient S structure, and the 6 comes from the fact that we have 2 things that we're interested in. We are interested in ux and uy. So there's 2 unknowns. So there's 3 nodes. For every node, there's 2 unknowns. So now this has 6 columns. If it was a quadrilateral, then this matrix will be a 3 by 8. So that's one thing to notice. In particular, for the constant strain triangle, this CST stands for constant strain triangle, the actual derivatives are very easy. They are just this difference between the nodal coordinates. You can see that these are all constant. There's no function of x on y. This only depends on, this is constant, only depends on nodal coordinates, but it doesn't change inside of the element. So that's the B matrix. If you put it in the into the integral, actually, because everything is constant, then this is just the area of the element times BE transpose times D times BE. Again, because everything is constant, the integral just gives you the area. And the D, I put it in the last class. I can write it. I don't know it by memory, but it's basically material properties. Again, this D has material properties. All right, for the force vector, this is what the force vector looks like if you know the force at the nodes. Just do a big if B equals Bx, By, is constant. If B is constant, then the force vector is just A over 3 times Bx, By, Bx, By, Bx, By. Finally, for the boundary attractions, I'm not gonna do this. I'll do it by hand, but similar to before, what you need to do is basically multiply the traction times the length of the element and then divide by 2 if it's constant traction. Here, if the traction changes, for example, between a point, then you can see that this is basically a linear interpolation of the traction. And you only apply it to the 2 nodes that basically are on that edge. So for example, here, this edge is the edge of nodes 1 and 2, and the traction in X goes from T1X to T2X. Then the traction for node 1 basically carries more weight from the TX1 and a little bit of TX2. You can think of that as a weighted average. Actually, let me do the constant case. So if traction is constant, so if the traction is constant in an edge, then all you would have would be L over 2 times Tx dy Tx dy 0, 0. And all I'm doing is basically multiplying the traction is force per unit length. I'm multiplying by the length of the edge, and then I'm just splitting it in 2. And I'm putting half of it to one node and half of it to the other node. And the reason why the third node doesn't have any is because the third node is not on that edge. So I only need to add it to the nodes that are on that edge. Questions? All right, so we'll actually do one example. So we have these 2 triangular elements. As we would define in Abacus. So the nodes are, 0, 0, 2, 0, 2, 1, 0, 1. The elements are 1, 2, 4, and 2, 3, 4. And then we are given, actually, in this case, sort of the solved problem. We are given the displacement at all nodes. So assume that we have already solved the problem. The question is, plot the displacement along the line shown in the figure, so y equals 0.5, and plot the strain along the line shown in the figure. So I'll give you 10 minutes to discuss, and I'll go around and I'll help you out. You will have to go to your notes to find the shape functions and their derivatives for the triangle. I'll help you out. but I would say do the have yellow, so it's going to pull the homework. Right. So, wait, yeah. Value of the display. That they should be. For sure, if you go to the yeah, so yes. Yeah. First primary and also secondary. Just start. They should be. I'll take some of the what is the just all you need to do is functions. That would be which sorry. And then you can set what it's going to be a function based on that. So you can just evaluate it. Just have to evaluate it as 5.5. And then it's just a function, right? And the same thing for any. Rather than do the shape function, but then the displacement just like I said, some of the shape functions. Which explains right? Explain so you can either do it like this. In the same. I would call it. That's ChatGPT. I'm obsessed with ChatGPT. All right, I think. Yes. On the strain, you don't need the, for the strain, you don't need the concentration. The strain, you just need the store of, but you just need to apply the B matrix and the XY, or at the size. So for the strain, you either multiply the B matrix, and B has basically the XY. 6 by 1 that has human negative y equals y, etc. Or that's maybe all you need is the derivative of the shape function. That's it. So that you don't, if you want the stress, then you need to multiply whatever this is by the image. That one does have. All right. All right. Let's do this so that we can finish. All right, I'm going to share my screen. Oh, wait, why is this? I would do it with code because I solve everything with code. By the way, I asked ChatGPT. You shouldn't trust it, see, because I asked ChatGPT to write a Python code to interpolate the displacement vector and strains in the constant strain triangle, and this is wrong. These are not the shape functions. This is completely wrong. So just to point out, as usual, it could be a useful tool if you know what you're doing. But for example, here, I asked it for the interpolation, and these shape functions are just completely wrong. So, which is why in the exam I usually have some ChatGPT question. You can use it. I don't have anything against using it if you know how to use it. For this, let me just create a copy. And so we have, I'm not gonna read the mesh. So actually I don't need this. I don't need this. The only reason why I have this is because this has already the shape functions for the triangle, and it has the gradients of the shape functions, which is what I want. So I don't have to do it by hand. This is what I want. Okay, so I'm gonna execute that and then forget about the rest. So what information do I have? I have these nodal coordinates, right? So it's node X. And if you just go to the example that I was just showing, do I have it here? Where do I have it? me find my own. I don't want to switch the screen here. So the coordinates are 0, 0, 2, 0, 2, 1, 0, 1. So 0, 0, 2, 0, 2, 1, 0, 1. Okay, so these are all the nodal coordinates, and then the elements are 1, 2, 4, 2, 3, 4, but I'll change the, so 1, 2, 4, but I'll do 1, 2, 4. I'll have to subtract 1 at the end, and then 2, 4. All right, so now I have the mesh, basically, the x coordinates and the elements. And so if I want the displacement, and I also have the displacements, right? So I also have node u. Oh, no, I'm gonna run out of time. So the displacements are 0, 0, 0, 0, minus 0.1, 0.1, 0.1, 0.1. 0, 0, 0, 0, minus 0.1, 0.1, 0.1, 0.1. All right, this is the information that I have. For element 1, I won't have time to do the whole thing, but for element 1, the displacement is actually a function of x and y. What is the displacement? It has an x component, which is evaluating n1 at some x and y, right? And I need to pick which x and y to evaluate. So for example, if I pick, it says that I want to evaluate at y equals 0.5. And for x, it wants to evaluate at multiple x's. So I would just create an x of, from 0 to, I think it goes to probably 1. Let's say 100 points. I won't be able to finish this today. So I'll just do it on Monday of next week. I just sketch this and then we go. So this is gonna look something like this. I'll finish it on Monday. Yeah, so let's stop right here. And then I'll finish this and do more examples on Monday. Good luck on Friday with the abacus exam.